row space, column space, and null space. This section, 4.7 and 4.8, they run together. Let me spend about 10 minutes here in this section, and then 4.8 is very quick, 5 minutes there. 4.7 is really, it starts off by trying to classify for us what we've really been looking at for this entire course. That is, you take a system, you write it as a matrix. What do those rows mean to the theory of matrices? What do the columns mean? So here we talk about the rows represent a row space. Like you got a vector space or subspace, those rows mean something. And then likewise, those columns also mean something. They form skeleton framework for building other systems, if you will. And so, if I have a matrix A, which here it has m rows, n columns, so the row vectors are in Rn. What does that mean? If you look at each row, they have n terms in them for each row. So the row vectors are in Rn, given there. The column vectors have m terms or components inside, right? So the row vectors would be in Rm. So now we can classify the so-called row space, column space, and the null space. We say that if you have a matrix, some m by n matrix, then the subspace of Rn span, we know what span means, span that produces, spanned by the row vectors of A, we call those vectors the row space of A. So basically, if I take a matrix, and if you can reduce that matrix down to its identity, if you look at the leading ones, for each row with a leading one, that original row is said to be in the row space. So the leading one is very important. Basically, the leading one kind of gets you back down to that skeleton form of zeros and ones. So if I can get the leading one, then that one in that row means that that row is very special. I can use that row to build other vectors. It becomes a part of the basis. The same thing happens for the matrix reduced to zeros and ones. If I have a 1 in that particular row that's reduced, that row is in the so-called row space, but also that same 1 in the row is also a position in the column. And that 1 tells us that that column is also in the column space. So the subspace of Rm spanned by the column vectors of A is called the column space. Now you remember that last problem we just got through doing, where the question was find the basis for the solution space for a homogeneous system? Well, we used all that terminology. That was the null space. In other words, if I take Ax equal to 0 and solve for that, then the basis that I get for that is called the null space. So here, the solution space of the homogeneous system, what's the homogeneous system? Ax equal to 0, that's what it means, which is also a subspace of Rn. Here we call, it's called here the null space. So that solution space for the homogeneous system, you can just say simply, that's the null space. Right? Very important theorem. It's called the superposition principle. You see it here in this class. You also see it in differential equations. I stated here there's a problem on the test that relates to that. It's going to be very straightforward. I think it should be also in the on the sample exam worked out for you. Very straightforward. I don't have time to go over it. I want to cover the row space, column space, and the null space down here for a problem that I want to work before you. But the superposition principle simply says is that any solution for Ax equal to b, so it says if x naught is a particular solution for Ax equal to b, that's for some b, like some vector b out there, And if S is a basis for the null space, the solution space for x equal to 0, then every solution of x equal to b. What does that mean, every solution? It means that, look, these b values can change. You fix the coefficient matrix A to be the same, but b can be different. So for every different b matrix you have out there, that's going to change the particular solution. But the general solution for x equal to b is said to be the linear combination of the particular solution plus its complementary solution. What's the complementary solution? The complementary solution is the solution for the null space. It's the solution for the when you set x equal to 0, and you can write those solutions as a linear combination of the basis for S. That's important. That's good stuff. That's good stuff. But these theorems here are classical. Every row operations do not change the null space. So it doesn't matter which way you want to reduce the matrix, the null space will stay the same. Every row operations will not change the row or the column space. So that's good to know. So if you do your system reduced a different way than somebody else, doesn't matter the way you reduce, the row space, the column space, the null space will stay the same. Another important theorem is that if a matrix R is in row echelon form, then the rows with the leading ones, I told you that the leading ones give us a great indicator of where the basis will be formed for that system, whether it's the basis for the row space or column space. So if a matrix R is reduced in row echelon form, then the rows with the leading ones form a basis for the row space, and the columns with leading ones also form a basis for the column space. The corollary that I thought was important, that I added in here myself, is that let A be a matrix reducible to row echelon form. The original corresponding rows or columns of A that corresponds to the rows with leading ones also form a basis for the row or column space. What is this theorem saying? This theorem is saying this, that if I have a matrix and I reduce that matrix down to row echelon form, and where I have the leading ones, then that result of the row reduced echelon form matrix, those leading ones, those rows give me a basis for the row space. But the corollary says, if I have a leading one in row 1, then the original row 1 is also a basis for the row space without even being reduced. As long as I know that that row reduces down to a leading 1 there for that particular row. Okay. Now I'm going to skip problems 1 and 2. I do not have those on the test. I took them off. And the problem that I do have on the test, this guy right here, I believe is on it, but I worked that one for you. Parts A and B, that's good stuff. Here's what I want to get to here. Find a basis for the null space and the row space for A. Now what we're going to do for this guy is I'm going to reduce this on my graphing calculator. So this is reduced to this is reduced to 1, 0, 0, 0, 1, 0, negative 16, negative 19, and 0. So I reduced this. The rows with the leading ones, they form a basis for the row space. So here, the basis for the row space (1, 0, negative 16, and 0, 1, negative 19. Now, to to get the basis for the null space, we do what we did in that previous problem in that previous section. That is, I take the matrix, so here to find the basis for the null space, simply solve for the set of infinitely many solutions. Because I get that. Because, see there, I have that last row that's all zeros. That tells me that I have infinitely many solutions. So here, what I have is let x sub 3 equal to t. And so I get, do you see that x sub 1 is equal to 16t? And x sub 2 is equal to 19t? Do you see that? Brother Luke, you see that? Okay, good. So then, this implies that x is equal to x sub 1, which is 16t, x sub 2, 19t, and x sub 3, which is t. That is, this is 16, 19, and 1 times t. So here, the basis for the null space is this vector 16, 19, and 1. Now I'm going to show you something. Now notice that the basis for the row space, there were two of those, right? And the basis for the null space is 1. 2 plus 1 is 3, right? This is a 3 by 3 matrix. It's going to be the idea. So if the basis for the null space was 2, and you have a 3 by 3, then the basis for the row space is going to be 1. 1 plus 2 is 3, right? Now the basis for the column space is going to be 2 as well, because the basis for the row space, the basis for the column space, it's going to be the same dimension. And I can just write that here for you. Here where I have the leading ones, I get a basis for its row and also column space. So we didn't ask for that, but I'll go ahead and put it in here. The basis for the column space, 1, 0, 0, 0, 1, 0. Part number B. If you reduce this, you get 1, 0, negative a half, 0, 0, 0, 0, 0, 0. Okay. There's only one basis for the row space, it's that first row, because that's the only one where I have a leading 1, right? So it's the basis for the row space. 1, 0, negative 1 half. Now the basis for the null space, that is when you set AX equal to 0. Here, I have to solve for the infinitely many solution set. Since I have a 0 at A22 and a 0 at A33, it tells me that x sub 2 is a parameter and x sub 3 is also a parameter. So we set x sub 2 equal to s, x sub 3 equal to t. Now x sub 1 is equal to 1/2 t. So x is equal to x sub 1, x sub 2, x sub 3. Well, x is 1/2 t, x sub 2 is s, x sub 3 is t. I'm going to group that. This is 0, 1, 0, just getting the s's first, plus the t's, 1/2, 0, and 1 times t. So here, my basis for the null space would be 0, 1, 0, and 1/2, 0, 1. How many do I have? I have 2. I have 2 for the basis for the null space. I have 1 for the basis for the row space. Again, 2 plus 1 is 3. Now, why am I saying that? The reason why I'm saying that is that the dimension of a particular space is called its rank. And so just give me 1 minute and I can teach you section 4.8 with the same idea, because basically I'm telling you 4.8 right now. So I'm through with this. The rank and the nullity. The rank is said to be the number, it's the number of how many vectors is in the row space. And the nullity is the number of vectors in the so-called null space. So it's almost like really that dimension is the rank, if you will. So just one problem, and I got it on the calculator, so it's already done. Here the question is, find the rank and nullity of the matrix A by reducing it to echelon form. All you do is take the matrix, reduce it to echelon form, and you get the answer. I took this matrix, I reduced it down, reduce this matrix down, and all you get is this. This is 1, 0, 0, 0. This is 2, 0, 0, 0. Negative 1, 0, 0, 0. 1, 0, 0, 0. Now the rank is the number of vectors in the row space. Well, the row space tells me that wherever I have a leading 1, you count that row for the basis. We only got one leading 1, right? So here the rank is 1. The rank of A is equal to 1. How many vectors do I have in that basis? The nullity is the number of vectors that I have in the so-called null space. Well, since my time is limited, notice here that this guy is a 4 by 4, right? It's a 4 by 4. So I'm expecting total number 4. So if I have the rank is 1, the nullity has to be 3, right? You're done. The nullity of A is equal to 3. Okay. Thank you.